Imagine a magic box. You drop a number in the top, a gear turns inside, and a new number pops out the bottom. That box is a function. The number you drop in is called the input. The number that comes out is the output. The most important rule is this: for every single input, the box must give you exactly one output. It can't give you two different answers for the same input. Think of a vending machine. You press button A4, and you always get the same chocolate bar. You never press A4 and sometimes get a chocolate bar and sometimes get a bag of chips. A function works the same way. One input, one output, every time. Why do we even care about this box? Because the world is full of relationships where one thing depends on another. If you know the rule, you can predict what will happen. Imagine you're saving money. Each week you add 100 rupees to your piggy bank. The total amount in the bank depends on the number of weeks that have passed. That's a function: weeks in, total savings out. Or think about driving a car at a steady speed. The distance you travel depends on how long you drive. Functions let us capture these if this, then what rules. They let us model a situation, make a prediction, and understand how changing one thing affects another. That's the whole purpose. Let's open the box and see how it works. We give our function a name, often just a letter like F. We write the input as x. The rule is what happens to x. We write it as f of x. For example, f of x equals x plus 2. The set of all numbers you are allowed to put in is called the domain. Think of it as the menu of a restaurant. You can only order what's on the menu. For our simple function, the domain is all real numbers. You can put in 3, you can put in -7, you can put in pi. The set of all numbers that can possibly come out is called the range. For f of x equals x plus 2, if you put in all real numbers, you'll get all real numbers back out. The function is a one-way journey from the domain to the range. Let's use our function idea to solve a real problem. What is the area of a square? You know the rule: area equals side length times side length, or s squared. This is a function. The input is the side length, which we'll call s. The output is the area, a. The rule is a of s equals s squared. Now, what's the domain? Can a square have a side length of -3 meters? No, that makes no sense in the real world. So our domain is all positive real numbers. What's the range? When you square a positive number, you always get a positive number back. So the range is also all positive real numbers. Let's find the area of a square with a side of 5 meters. We put 5 into our function. 5 squared is 25. The output is 25 square meters. The function took our input, applied the rule, and gave us exactly one output. Imagine you have a magic box, a function machine. You drop in a number, it does something to it, and out pops a result. Now, what if you could run that machine backwards? You feed in the result, and it spits out the original number you started with. That's exactly what an inverse function is. It's the undo button for a function. If our original function f takes an input and turns it into an output b, then the inverse function, written as f to the -1 of x, takes b and gives you back the. A super important warning right away, that little -1 is just a symbol. It does not mean 1 divided by f of x, like a reciprocal. It's just the name we give to the backwards machine. Why would we ever want to run a machine backwards? Think about putting on socks and then shoes. The function is getting ready. The output is having your shoes on. But later, you need to undo that process. You can't just take off your socks first, your shoes are in the way. The inverse process is taking off your shoes and then your socks. It reverses the order perfectly to get back to the starting state. In math, this is how we solve equations. If a function tells you the effect, the inverse function helps you find the cause. If you know your final bank balance after some interest was added, the inverse tells you what you started with. It answers the question, what input produced this specific output? So how does this backwards machine actually work? A function is just a set of ordered pairs, linking each input to its one and only output. To build the inverse, you simply swap every single pair. The output becomes the new input, and the original input becomes the new output. If you look at a graph, this swap has a beautiful visual effect. The point with coordinates A, B becomes the point B, A. This is exactly the same as reflecting the entire graph over a diagonal line, the line y equals x. It's like folding the graph paper along that line. But here's a crucial catch, you can only do this perfectly if the original function never gave the same output to two different inputs. If it did, the inverse wouldn't know which one to go back to. A function that passes this test is called one-to-one. Let's make this concrete with a real-world example you see on weather apps. We have a function that converts a temperature from Celsius to Fahrenheit. The rule is, multiply the Celsius temperature by 9/5 and then add 32. So, if it's a boiling hot day at 100 degrees Celsius, the function does 9/5 times 100, which is 180, plus 32, giving us 212 degrees Fahrenheit. Now, what if a friend abroad tells you it's a chilly 50 degrees Fahrenheit, and you want to know what that is in Celsius? You need the inverse function. To undo the original steps, you must reverse the order. The last thing the original function did was add 32. So, the first thing the inverse does is subtract 32. The original function first multiplied by 9/5. So, the inverse must then divide by 9/5, which is the same as multiplying by its reciprocal, 5/9. Our new rule is, subtract 32, then multiply by 5/9. Let's test it. Imagine you have the graph of a function drawn on a piece of paper. The horizontal line test is a simple trick you can do with your eyes. You picture drawing horizontal lines, flat lines that go left and right, all the way up and down the graph. If you can find even one horizontal line that cuts through the graph in two or more different places, then the function does not have an inverse. It is that straightforward. The test answers one question: does this function ever send two different inputs to the exact same output? If it does, you cannot undo it uniquely, so no inverse exists. We already know that an inverse function is like a perfect undo button. You put in an output, and it tells you the one and only input that produced it. But if two different inputs both give you the same output, say both 2 and -2 give you 4, then when you try to undo 4, you are stuck. Which one was it? The horizontal line test is valuable because it instantly shows you whether that problem exists anywhere on the graph. It is a visual shortcut for checking the one-to-one property without doing any algebra. If a horizontal line hits the graph twice, those 2 points share the same y value, meaning the function is not one-to-one, and its inverse would not be a proper function. A function is called one-to-one when every y value in its range is paired with exactly one x value from its domain. Think of it as a perfect pairing, like dance partners where nobody is left out and nobody has two partners. Let us see why y equals x squared fails the test. Pick y equals 4. The graph shows it came from x equals 2 and also from x equals -2. A horizontal line at height 4 cuts the parabola in two places. That means the function is not one-to-one. Now look at y equals x cubed. As x grows, y grows. As x goes negative, y goes negative. Every horizontal line hits the curve exactly once. It is 1-to-1, so it has an inverse. But here is a powerful idea. We can take a function that fails, like x squared, and restrict its domain. If we only allow x values that are 0 or positive, we chop off the left side of the parabola. Let us solve a concrete problem. Suppose a machine squares any number you feed it. If I tell you the output was 9, can you uniquely tell me the input? You might say 3, but -3 also gives 9. The horizontal line test on the graph of y equals x squared shows a line at y equals 9 hitting the curve at x equals 3 and x equals -3. So, the full parabola does not have an inverse. But in many real situations, like measuring the side length of a square from its area, we only care about positive lengths. So we restrict the domain to x greater than or equal to 0. Now the graph is only the right half of the parabola. A horizontal line at y equals 9 hits it only at x equals 3. The inverse function is the square root of x. We test it, the square root of 9 is 3. It works perfectly. We already know an inverse function undoes the original function. Now we learn the algebraic method to actually find that inverse. The core idea is beautifully simple. We start by writing our function as y equals f of x. Then we swap the roles of x and y everywhere. This swap is the algebraic version of reflecting a graph across the line y equals x. Finally, we solve this new equation for y. That new y is our inverse function, written f inverse of x. It's like a recipe: write, swap, solve. Why do we swap x and y? It's not just a trick. It directly shows a deep truth: the domain of the original function becomes the range of the inverse, and the range becomes the domain. The original function takes an input from its domain and gives an output in its range. The inverse must take that output as its input and give back the original input. Swapping x and y makes this trade happen. Geometrically, every point A, B on the original graph becomes the point B, or on the inverse graph. This is exactly a reflection across the diagonal line y equals x. The graph of the inverse is the mirror image of the original graph over that line. Let's walk through the steps for a simple function, f of x equals 2x plus 3. First, write it as y equals 2x plus 3. Second, swap x and y. This gives us x equals 2y plus 3. Now we solve for the new y, subtract 3 from both sides to get x minus 3 equals 2y. Then divide by 2. We find y equals x minus 3 over 2. This is our inverse function. Let's try a slightly harder one, f of x equals x minus 1 over x plus 2. Write y equals x minus 1 over x plus 2. Swap to get x equals y minus 1 over y plus 2. To solve, multiply both sides by y plus 2. Distribute x, bring y terms to one side, factor out y, and finally divide. The inverse is f inverse of x equals 1 plus 2x over 1 minus x. Let's use this in a real situation. You're traveling and see a temperature of 77 degrees Fahrenheit. You want Celsius. The formula to go from Celsius to Fahrenheit is f equals 9/5 c plus 32. This is our function f of c. To find the inverse, we write f equals 9/5 c plus 32. Swap the variables, c equals 9/5 f plus 32. Wait, that's not right. The variables represent quantities, so we swap their roles. Actually, we want a formula that takes Fahrenheit and gives Celsius. So we write the original as f equals 9/5 c plus 32. Now swap the letters. C equals 9/5 f plus 32. No, the swap means we treat the old output f as the new input. So we write f as the input and c as the output. Let's do it carefully. Original, output f equals 9/5 times input c plus 32. To invert, we solve for c, subtract 32, f minus 32 equals 9/5 c. You already know that an inverse function undoes the original. If f takes x to y, then its inverse g takes y back to x. Now we ask a new question: how fast does the inverse change? That is, what is the slope of the inverse function at a point? The answer is beautifully simple. The slope of the inverse at y is just 1 over the slope of the original at the matching x. In symbols, g' of y equals 1 over f' of x, where y equals f of x. It is a reciprocal relationship. Think of it like this: if f is steep, its inverse is flat, and vice versa. Why do we care about this reciprocal slope rule? Because some inverse functions are very hard to differentiate directly. Take the natural log, ln x. Its formula is complicated, but we know it is the inverse of e to the x. And e to the x has a beautifully simple derivative. It is its own derivative. So we can use the reciprocal rule to find the derivative of ln x without messy algebra. The same trick works for inverse trig functions like arcsin and arctan. This rule is a master key that opens the door to differentiating a whole family of functions that would otherwise be locked away. Where does this reciprocal rule come from? Picture the graph of f and its inverse g. You already know that g is the reflection of f across the line y equals x. Now pick a point on f and draw the tangent line there. Its slope is rise over run. Reflect that tangent line across y equals x. What happens? The rise of the original becomes the run of the reflected line, and the run becomes the rise. So the slope of the reflected line is run over rise, which is exactly 1 over the original slope. Since the reflected line is the tangent to the inverse function, we get g' of y equals 1 over f' of x. It is all just geometry. Let's use this rule to find the derivative of the natural log. We know ln x is the inverse of e to the x. So set f of x equal to e to the x, and its inverse g of y equals ln y. The derivative of e to the x is itself e to the x. Now pick a concrete point. Let y equal 2. Then x is ln 2, because e to the ln 2 is 2. At this x, f' of x is e to the ln 2, which is just 2. By our reciprocal rule, g' of 2 is 1 over f' of x, so 1 over 2. In general, for any y, g' of y is 1 over e to the ln y, which is 1 over y. So the derivative of ln x is 1 over x. That is the power of the inverse function rule. We know sine, cosine, and tangent take an angle and give us a ratio. But what if we know the ratio and need the angle? That's exactly what inverse trig functions do. They are the undo buttons for sine, cosine, and tangent. The function arcsin, for example, takes a number between -1 and 1 and returns the angle whose sine is that number. The name literally means the arc whose sine is. So arcsin of 0.5 is the angle whose sine is 0.5. We also have arccos and arctan, which work the same way for cosine and tangent. Imagine you're looking at a tall building. You know you're standing 50 meters away, and the top of the building lines up with a point 80 meters high on a nearby crane. You can easily find the tangent of the angle to the top. It's 80 divided by 50, which is 1.6. But what is the angle itself? You can't build a ramp or aim a laser without knowing the angle. This is the core problem inverse trig functions solve, turning a known ratio back into the angle. They are the bridge from the world of ratios, which are easy to measure, back to the world of angles, which we need for construction, navigation, and physics. You might remember that a function must be one-to-one to have an inverse. But sine, cosine, and tangent are not one-to-one, they repeat their values. So we restrict their domains to a small piece where they pass the horizontal line test. For sine, we use angles from -π/2 to π/2. For cosine, we use 0 to π. For tangent, we use the same as sine. This gives us the official arcsin, arccos, and arctan functions. Their graphs are just the original trig graphs reflected across the line y equals x. Now, to find the derivative of arcsin x, we use the reciprocal slope rule from the last chapter. The derivative is 1 over the derivative of sine, evaluated at the angle. That gives 1 over cosine of the angle. But we need the answer in terms of x, not the angle. Here's where a right triangle comes alive. Let's solve a concrete problem. You're building a wheelchair ramp. Safety rules say the slope must be exactly a 3:4 ratio, meaning it rises 3 feet for every 4 feet of horizontal run. What angle should you cut the supports? We know the tangent of the angle is the rise over the run, which is 3/4, or 0.75. To find the angle, we use the arctan function. So theta equals arctan of 0.75. When we calculate this, we get an angle of about 36.87 degrees. This is the exact angle you need to set your saw. The same method works for any right triangle problem. If you know two sides, you can find any angle using the inverse trig function that matches the sides you have. Imagine you have a secret message and a special ring that scrambles each letter into a code. That scrambling is a function. The inverse function is the ring that turns the code back into the original message. In the real world, encryption is just a function that takes your plain text and turns it into gibberish. Decryption is its inverse, taking the gibberish and giving you back the plain text. Another everyday example is temperature. A function converts Celsius to Fahrenheit. Its inverse does the opposite, converting Fahrenheit back to Celsius. So an inverse function is simply the tool that reverses a process, taking the output and giving you back the original input. Often in life, you know the result but need to find what caused it. You see a bank balance and want to know how long the money was invested. You feel the heat and want to know the Celsius temperature from a Fahrenheit reading. This is exactly the problem inverse functions were invented to solve. If a function takes a cause and gives you an effect, its inverse takes the effect and gives you back the cause. For example, if you have a model for population growth that tells you the population after a certain number of years, the inverse function tells you how many years it took to reach a certain population. It lets you reverse any one-to-one process, which is incredibly powerful for solving real equations. Let's see how this works with a simple encryption. Imagine a shift cipher where we replace each letter with the 1 3 places after it. Mathematically, this is the function f of x equals x plus 3. To decrypt, we need the inverse function. We swap the input and output and solve for the new output. Starting with y equals x plus 3, we swap to get x equals y plus 3, and solve for y to get y equals x minus 3. So the decryption function, the inverse, is f inverse of x equals x minus 3. For temperature, the function to convert Celsius to Fahrenheit is f equals 9/5 c plus 32. To find the inverse, we swap c and f to get c equals 9/5 f plus 32, then solve for f. We subtract 32 and multiply by 5/9, giving us the inverse function, c equals 5/9 times f minus 32. This is how we build the reverse process step by step. Let's solve a real problem. Suppose you invest money at a 5% continuous annual interest rate. The amount after t years is given by the exponential function a equals p times e to the power of 0.05 t, where p is the starting amount. You want to know how long it takes for your money to double. So we need the inverse of this exponential function. We set a over p equal to 2, giving us 2 equals e to the 0.05 t. To undo the exponential, we apply its inverse, the natural log. Taking the natural log of both sides gives us ln of 2 equals 0.05 t. Finally, we solve for t by dividing by 0.05. The natural log of 2 is about 0.693, so t is about 13.9 years. The inverse function let us solve for the input time directly from the output amount.